Okay, let's just dive right into this explainer. We're going to be exploring the hidden mechanics that dictate how light interacts with our world. I mean, we see light every single day, right? But the way it actually bends and overlaps and paints our reality, it's literally nothing short of extraordinary. So today, we're going to crack the code on optical interference. Just look closely at the brilliant shifting blue of this morpho butterfly. Now, here's the wild part. It isn't made of pigment. If you were to somehow grind up this wing, you actually wouldn't find any blue ink at all. Instead, it's a complete structural illusion. That arresting blue color is caused entirely by the interference of light reflecting off these tiny microscopic structures. And, this brings us to a really fascinating question, one that's going to frame our entire journey today. How exactly does light, interacting with itself, act as the fundamental source code behind this natural hologram? Well, to answer that, we kind of have to rethink everything we know about how light actually travels. So here's our blueprint for today's explainer. We'll start with Section 1, light as a wave, then Section 2, Young's double-slit experiment, Section 3, calculating interference with phasors, Section 4, thin film interference, and finally, Section 5, the Michelson interferometer. All right, Section 1, light as a wave. Okay, so to really understand this, we first need to totally abandon the simple idea of geometrical rays and travel all the way back to 1678. Dutch physicist Christian Huygens brilliantly theorized that a light wave doesn't just, shoot forward like an arrow. Instead, it propagates forward as this endless glowing series of spherical secondary wavelets. It's kind of like dropping a pebble in a pond, but imagine that every single point on that rippling wave acts as a brand new pebble, creating its own ripples. Pretty wild, right? So the absolutely crucial point here is that when a wavefront hits a new, denser medium, say going from air into glass, its speed actually drops. And because the frequency of the light remains absolutely locked in, the wavelength is forced to shrink. This difference in speed right across the wavefront causes the wave to bend, and that's a process we call refraction. Moving right along to Section 2, Young's double-slit experiment. Fast forward to 1801, and Thomas Young decisively proved this wave theory. At a time when most scientists still firmly believed light was purely a stream of particles, Young created a phenomenon that completely defied that idea. Just as water waves diffract or flare out as they pass through a narrow barrier, light does the exact same thing. When coherent light flares through two narrow slits, those overlapping waves create a beautiful glowing pattern of bright and dark fringes on a screen. Particles absolutely wouldn't do this. Only overlapping waves can pull that off. So here's the secret behind those fringes. As the waves travel from those two slits to a point on the screen, they actually travel different distances. If they travel different distances but arrive perfectly in step, meaning their path difference is a perfect integer, like 1 or 2 full wavelengths, they amplify into a bright fringe. We call this constructive interference. But if they're off by exactly half a wavelength, the peak of one wave literally meets the valley of another, and they completely cancel each other out into total darkness. Now, the exact location of these neon-lit fringes on our viewing screen is determined purely by this geometric path length difference. In this really elegant equation, d is simply the distance between the slits, and theta is the angle to the screen. By plugging in different integers for m, we can map out a perfectly structured interference pattern of alternating light and dark bands. It's basically a mathematical blueprint for the light. All right, Section 3. Calculating interference with phasors. Now that we've actually proven the phenomenon of interference exists, let's look at how we calculate the exact intensity of these overlapping waves. But before we dive into the math, there's a really vital rule. To reliably calculate and actually see these patterns, our light sources must be completely coherent. That just means their phase difference is permanently locked in time. Lasers produce highly coherent light. Sunlight, or say a standard light bulb, however, is totally incoherent. Its phase shifts randomly, which is exactly why we don't see crazy psychedelic interference fringes every time we turn on a lamp in our living room. To calculate the overlap of these coherent waves, physicists use a really clever tool called a phasor. Try to visualize it as a sweeping radar vector on a digital grid. The length of the arm represents the wave's amplitude, and the speed it spins perfectly matches the wave's frequency. This visual tool helps us easily sum up multiple waves, even if their amplitudes are completely different, just by adding the vectors head to tail. And by adding these rotating vectors, we get this incredibly sleek intensity equation.
It basically proves that the final brightness on our screen is driven entirely by the phase difference, which is represented by the Greek letter phi. If the phase difference is 0, that cosine term maximizes, giving us a brilliantly bright fringe. But if it's 180 degrees, the cosine drops all the way to 0, giving us total darkness.
Next up, Section 4, Thin Film Interference. Okay, let's bring all this math back to the real world and finally solve the mystery of that color-shifting butterfly from the very beginning of our explainer. You see, the morpho butterfly's wing is covered in these microscopic scales that act as a thin film. It's actually very much like the air gap between lenses that creates those famous circular patterns known as Newton's rings. When white light hits the wing, some of that light reflects off the top surface of this microscopic film, while some of it passes right through and reflects off the bottom surface. Then, those two reflected light waves interfere with one another. Now, when we're calculating this thin film interference, we use this handy table to remember one absolute rule of thumb. Reflecting off a medium with a higher refractive index shifts the wave by exactly half a wavelength. So depending on the precise thickness of the butterfly's wing scales, only specific wavelengths, specifically that vibrant blue, interfere constructively. And as your viewing angle changes, the path length difference changes too, which causes the color to just magically shift right before your eyes. And finally, Section 5, the Michelson interferometer. Harnessed by A.A. Michelson back in 1881, this incredible instrument basically takes a single light beam and hits a beam splitter, sending half the light down one arm and half down another. The light then bounces off mirrors at the end of each arm and recombines right at a detector. By very, very slightly moving just one of those mirrors, we change the path length of one arm, and we can actually watch the bright and dark interference fringes shift in real time. It's so cool. And here is why this is such a game changer. By simply counting the number of shifting fringes using this equation, scientists can measure physical distances down to the microscopic scale of a single wavelength of light. Think about that. It's literally a ruler made entirely out of light waves, allowing for unprecedented precision in modern engineering and physics. Which leaves us with a final, kind of provocative thought. If understanding these overlapping waves can map the microscopic world, what other cosmic secrets are just waiting to be decoded in the interference of light? The exact same principles we just talked about are what modern astronomers use today to measure the expansion of the universe and even detect gravitational waves from colliding black holes. The blueprint of light truly connects the microscopic all the way to the cosmic. Thanks so much for exploring this with me.